All right, got that going. Okay, so yesterday we started with special relativity. We derived our Lorentz transformations.
Yeah.
So our Lorentz transformations were how to go from one coordinate system to another coordinate system, right? So straight up, Galileo made me draw our picture really quick for the two reference frames we're talking about. So this is your reference frame. Here's me in your reference frame, if I'm moving along. So I'm at x equals vt. Remember in physics, we do our coordinate system's a little weird. We're used to xt. I always put the x on the right side, and the t at top. So a little bit weird there. So the steeper, or the shallower the line, the faster it's going. So a slow velocity would be like this. A fast velocity would be like this.
Oh, I see.
Right? Okay, so we have, and here's you in your coordinate system. You are always at coordinate 0. You don't move in your coordinate system. You call your center u. So you're at x equal to 0 and x equals vt. Over in my picture of what the world looks like, picture's taking up all the space. Over in my picture of what the world looks like using x prime coordinates and t prime coordinates, I'm over here, right there. So this is x prime equals 0. That's me. And then you would look something like this, which would be x prime equals minus vt. Right?
Yeah.
Right? So this is for, I'm going like this, watching you guys go back. So in your reference frame it looks like this, in my reference frame it looks like this. We're assuming constant velocity and we're both inertial reference frames.
Okay.
Right? Now Galileo said to do the transformation to get x prime coordinates from your coordinates. So if you say, oh, here's what the coordinates are in my picture, what must they be over here? How do we make that calculation? So I just want you to get intuition for this rather than just seeing it with the math. But let's say I hold an object at the end of this meter stick in front of me. So it's exactly 1 meter in front of me. Okay? And I'm walking. You with me?
Mm-hmm.
We want to talk about where that point is in your reference frame.
It would just be 1 meter ahead of you.
1 meter ahead of me. So here's what good old Galileo said. So if the object would have fallen out this path in your reference frame, right?
Mm-hmm.
1 meter ahead. So if it's right here, and since this is what I call 0, this is my 0, then however far ahead of me it is right there, that's going to be what the coordinate I assign to x prime. I say it's 1 meter ahead of me. My reference frame stays 1 meter ahead of me.
Oh, I see.
Right?
Yeah.
So it's going to be that distance ahead of me, but then what is this distance right here?
Yeah, your VT.
VT. So you know that the position you assign to it is equal to the position I assign to it plus VT.
Okay.
Pretty straightforward. Okay. So from this, we get our two transformation equations. Our first transformation equation, if we want to go from your coordinates to my coordinates, just solve for x prime. X prime is equal to x minus vt. Move the vt over there.
Yeah.
Or x is equal to x prime plus vt. We would put that over here. That's how we get your coordinates for mine. Right?
Mm-hmm.
Good so far? And also good old Galileo, he said in time is time. So what do I call time? Same thing you call time. And what do you call time? Same thing I call time. So that was Galileo. And we saw that this is a broken worldview. It leads to us seeing different speeds of light.
Yeah.
Law of physics, we all see the same speed of light. So something was wrong, something had to give. So Einstein got to work, and he says, No, actually, to get the x prime, if you want to get x prime, it's going to be x minus vt all over the square root of 1 minus v squared over c squared.
Yeah.
And to get the t prime, it's going to equal t minus v over c squared times x all over the square root of 1 minus v squared over c squared. Right? And then the only difference between these equations and the ones we write over here is switch your minuses to pluses in the bottom top.
And your x prime and your t primes, right?
Yeah. Okay. Now, we're always going to be working in pictures where we're using light seconds and seconds. And so the speed of light in all the equations that we're going to use is going to be 1. So the Lorentz transformations that we're going to be using are going to be x prime is equal to x minus vt all over the square root of 1 minus v squared, and t prime is equal to t minus vx all over the square root of 1 minus v squared. Just keeps it cleaner, so we don't have to worry about all the c's.
Yeah.
Okay, and we used this last time to talk about length contractions and time contractions. And we came to the conclusion that what I call second, you don't necessarily call second, and that what I call meter, you don't necessarily call meter.
Yeah.
And that's where we ended. Okay, so we're going to come up with these here again, and we're going to come at this with a completely different approach to help you see an analogy between how space and time are relative and what's not relative with geometry. And we're going to look at an analogy in Euclidean geometry. So now we're going over to Euclidean geometry. These are not space-time diagrams. This is Euclidean geometry, regular Euclidean geometry. And we have two reference frames here. Your reference frame, you talk about coordinates in terms of x and y. Now my reference frame is going to be rotated from your reference frame by some angle theta. And so I'm going to assign coordinates x prime, y prime to a point. So the point we're interested in is this point P. Let's make it red to make it clear. Everything else on here is just scribbles to help me show you something. There's a point that we're interested in. So yours is the blue reference frame. You say it's x to the right, y up. Mine's the purple reference frame. I say no, 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 it's x prime to the right and y prime up. You with me so far?
Yeah.
I think I have a scribbled out example. So, just to give one quick scribbled example, that will probably look awful. But so your coordinates could look like this. My reference frame could be rotated. We could be, it's terrible. So steep. We could be talking about some point, and let's say that the point in your reference frame is 3, 4. So you say this is the point. Three up, 4 over. You say it's 3, 4. Those are the coordinates you assign the point. Now I say, no, no, no. This is dot, 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 dot comes down. And I say it's 2 squared to 5 this way. And I say it's square root of 5 this way. So this is x, y, this is y prime, x prime. So I assign this thing the coordinates 2 squared to 5 and square root of 5. Now, who's right, who's wrong? What are the coordinates of that point?
3, 4 looks better.
3, 4 looks better. And the numbers came out nicer. But what are the coordinates of that point?
It depends on your reference frame.
Depends on your reference frame. In other words, the coordinates are relative.
Yeah.
Coordinates are relative?
Yes, coordinates are relative.
Okay.
That's what coordinates do. They give you its position relative to some origin.
Yeah, but the point is a point, right?
So talking about what is this thing's x-coordinate doesn't make sense. It doesn't have a definite x-coordinate, right?
Okay.
And talking about its y-coordinate doesn't make sense. It doesn't have a definite y-coordinate. Which of those are the right coordinates? But what can we say about it?
You can say that the point's there.
We can say that the point's there, but if my reference frame is just a rotation of your reference frame,
Oh, then there's a line that draws in between them.
then this line right here, what about this line?
It's the radius of a circle.
We should agree on its distance.
Yeah.
We can argue about its x-coordinates, we can argue about its y-coordinates, but we'll both agree about its distance. If you calculate 3 squared plus 4 squared, and then take its square root, you're going to get 5.
Okay.
If you calculate 2 squared to 5 squared, and the square root of 5 squared, you're going to get, and take its square root, you're going to get 5.
Yeah.
And so we can argue about the coordinates, but we'll always agree about the distance if my reference frame is guaranteed to just be a rotation from your reference frame.
Okay, that makes sense.
Good? And it turns out that that is an apt analogy for what is going on in special relativity. That somehow changing my velocity is like a rotation of coordinate systems. And while it changes the way that we see time, and it changes the way that we see distances, there's some quantity that we call the space-time distance, or the proper time, or the proper distance. You'll understand why we call it two different things in a second.
Okay.
That everyone agrees on. And it's a lot like this distance here. Everyone agrees on this distance. There's a proper time that everyone agrees upon in special relativity.
So there is like some sort of time that is.
There is, well, that's just what's called. There's some sort of distance that everyone agrees upon.
Distance from what?
From the origin, from where you and I intersect.
Okay.
There's a way that we can calculate distances from there. We'll use a different way of calculating distances than what you're used to in Euclidean geometry. In Euclidean geometry, we use circles to talk about distances. If I have a point, and I draw a circle around that circle is all the points equidistant from that point. We're going to be in a hyperbolic geometry. A hyperbolic geometry means all the points equidistant from a point are on a hyperbola.
What's a hyperbola again?
A hyperbola? You don't know your conic sections?
What?
You don't know conic sections? Holy cow. Okay, this is big enough that we need to take a side note for it. Conic sections. A cone. So you've got the cone that meets itself at the nose. Goes on forever.
Cone that goes on forever.
So the cones go on forever. And I'll try and bring some 3D elements to it. So there's that. There's that. Excuse me. Two cones meet at the nose, expanding forever in both directions. You think you see the picture I'm trying to say?
Yeah.
Okay. Now, take any random intersection of that cone that you want, and you are going to get one of three shapes, roughly speaking. If we say a circle is a special type of ellipse. You're either going to get an ellipse, you're going to get a parabola, or you're going to get a hyperbola. Those are the three possible combinations for any way you split this thing.
Okay.
So if I were to perfectly slit it like this, take an intersection like that, right across, then where it intersects that cone would be
Circle.
a circle. You see that? Now if I intersect the cone on a little bit of an angle, so I kind of intersect the cone, it's hard to do 3D. If I intersect on kind of an angle, now I'm going to get an ellipse. You with me?
Mm-hmm.
Now if I intersect it, how's the best way to do this one? intersect it parallel to this line right here, going up this way forever.
Okay.
Sorry, you understand what I'm saying?
Mm-hmm.
So it only ever intersects the top half, never intersects the bottom half of the cone.
Okay.
Then we get a parabola.
Parabola. I don't see that.
Is that because it goes on?
A parabola looks like this. The intersection would look like this. Here's where it's wrapped on that cone, and it gets wider and wider as the cone grows.
But doesn't it go to a sharp end?
No, the cone is rounded.
So it's like an hourglass.
So no, it's a cone, but it's a cross section of a cone. I don't know. Need something something bendy. Just piece of paper. You got one of your tests I can draw on the back of? So if we try and set this up as a cone, which will be kind of hard to do, and I start drawing on it parallel to this, it's going to be curved out right there.
What about the inside?
The cone's hollow.
Oh.
Cone is hollow. So your shape would exist completely on the surface.
Oh, well then, yeah, that makes sense.
Okay.
I thought your cone was like, some sort of like steel cone or something.
No.
Okay.
So the cone is just a surface. Take a piece of the surface, or in other words, draw a line on the surface. What did you draw? And so if we draw a line and say parallel to that, then we'd end up with a parabola. Now the last way we can cut it is we can cut it so that it intersects both the top and the bottom.
Right down the middle.
Isn't that how that was?
So I could do a cut like right here.
Oh.
Now what's that going to look like? That is going to look like what we call a hyperbola. So there's going to be a big gap where there's nothing, and then we're going to get something at the top.
Yeah.
So we'll have something at the top, and we'll have something at the bottom, and that's a hyperbola. Wow, that was awful. Let me draw a half-decent one for a second, just because I can try and get you interested early on for the metric we're going to be talking about. Just to actually have some dotted lines first. Because the hyperbola should get closer and closer to those lines. Never actually meeting them. So here's one hyperbola. From here on out, I'm just going to draw the top halves of the hyperbola. You with me?
Mm-hmm.
So there's a hyperbola. I could draw another hyperbola higher up, so that hyperbola would look something like this, right? And I could draw another hyperbola higher up, and that one might look something like this. You with me?
Yeah.
And so, the same way that in regular Euclidean geometry, if I had a bunch of concentric circles, those were all meant to be centered around some point. I know that they're not, that was awful. If all these circles were centered around this point, then each circle represents all the points equidistant from that center point,
Yes.
right? In a hyperbolic geometry like this, all the points on a hyperbola are equidistant from the center.
What?
So this point and this point are the same distance from the center.
No, they're not.
I know what you're saying. You are using circles to determine how close points are.
Well, if you just draw a line in between those two, yeah.
You're trying to impose Euclidean geometry on it.
So you can't draw lines?
It doesn't work the way you want it to work.
Other units. Other units on
That doesn't make sense.
This is not a flat surface. It's just a drawing. All right,
I can
so
start to see it.
here's what it is. All the points on a hyperbola are equidistant from here.
Even though they're going to infinity?
Even as they're going to infinity, yes. So I'm giving you intuition for where we're headed, and then we'll see this pop up. And that's the weird thing going on, is this is a type of metric that we have to use in space-time to talk about how far away a point is.
Okay.
And rough intuition, roughly speaking, the closer it is in time, or the further away in distance, the closer it is. And let me give you some intuition. This is terrible intuition, but rough intuition that might help. What is easier, for you to get to my apartment in 10 hours, or for you to get to this marker in half a second? Huh?
The marker.
Go! You missed it. Could you get to my apartment in 10 hours?
Yeah.
You have half a second to get to this marker. Go! You failed. Which one's harder? Harder.
Yeah, how do you say which one's harder?
It would be real easy for you. If I say, I'll bet you $10 million, we're going to make a bet.
Okay.
If you can get to this marker in half a second, I owe you $1 million. If I can get to my apartment in the next 10 hours, you owe me $1 million. Will you take the bet?
No.
Okay, we're just playing on your intuition here.
Okay.
That is because my apartment 10 hours from now is closer, easier to get to, closer in this metric than this marker is to you a half a second from now.
Is the top time and is the
Yes. Same as this.
Oh, so it's not like yx?
Distance.
well,
Yeah.
find the max of this.
Huh?
How do you draw a formula?
We'll get to formulas for a second. I'm just trying to give you intuition for where we're going. You know, give you that first introduction, then we did the math, then when you see it again, hopefully, click.
Okay.
I hope so.
I
Let's
hope
go
so
with
too.
it.
Okay. So, probably jumped too far ahead. Probably should have come to this a lot slower. Anyways, so back to this picture. You and I will disagree about our x coordinates and we'll disagree about our y coordinates, but we'll agree about our distances. We will always agree that whatever you call x squared plus y squared, I will call x prime squared plus y prime squared.
Yeah, that makes sense.
And so no matter how you rotate this, no matter how you rotate my reference frame with respect to your reference frame, this equation right here will always hold. And so that's what we call an invariant.
Invariant?
An invariant. It does not depend on your reference frame. It doesn't vary with your reference frame. This is a constant, whatever that quantity is.
Okay, that makes sense.
Good?
Mm-hmm.
Okay. So we're going to come up with some similar quantity for space-time. So first, now let's go back to this diagram. This diagram, we'll see if I can pull this off. It gets real messy. But, so I've got, you're the blue frame, I'm the purple frame. Here's our point P. I say that the coordinates of that point are x prime, y prime. You say no, it's xy. So I say it's x prime, here's my x coordinate, y prime, here's my y coordinate. You say no, it's x, y.
Okay, that makes sense.
Now, we want to do something similar with these Lorentz transformations, but just in plain old Euclidean geometry where you know how to easily talk about distances. And so we need to figure out how to get my reference frame from your reference frame. That's what we're going to try and do.
Well, wouldn't you use the distance like you just showed us?
So x prime is equal to, no, you need to figure out what this x prime is.
Oh,
You know x, you know how much I'm rotated theta. Your job now is to find x prime. And this theta in this scenario is going to act a lot like velocity does for us in our scenario.
okay, I see.
So, rotate some angle theta. So you know that this is at point x, y. What is it for me? You know it's x prime, y prime, y prime. But now we need to figure out what those distances are. You with me?
Mm-hmm.
Okay, so let's see. For x prime, it's going to be this distance plus this distance. Right?
Okay, that makes sense.
Let me get my pictures up here, see if we can remember how to calculate all these. So let's start with this distance. So x prime, it's going to be OA, whatever that length is. Maybe get our strategy up here. The length of OA plus,
A to x naught or prime.
yeah, A to x prime, we don't really have that point labeled, but I think we'll understand what we mean. Right?
Yeah, that makes sense.
Can you just
Okay.
write O to x prime?
So O to A, that one's easy,
Mm-hmm.
because that is just going to be the cosine of O to x, which is just has distance x.
Yeah.
You follow that? So O to A, that one's pretty easy. That one is going to be, the hypotenuse of our triangle has distance x, so it's going to be x times cosine theta. So I get this distance. Okay. Now, I need this distance, right?
Yeah.
Which is the same as this distance up here.
So C.
That's the same as that. And, oh, that's y prime. Let's see. I know this right here is y. Oh, wonderful. You see that?
How do you know it's y?
Right here.
Yeah.
That's y. We're going to talk about this right triangle. So if this side is y, then this side right here is going to be
So-
y sine of theta.
Yeah.
Perfect.
Do you know why?
Hmm?
Do we know why?
Yeah, you know the coordinates you assigned at x, y. You're trying to figure out the coordinates I assigned at x prime, y prime.
Okay.
Make sense?
Mm-hmm.
And you also know the angle I'm rotated by, relative to you. X cosine of theta plus y sine theta. Okay, we got that one right. All right, so now let's look for y prime. Y prime is going to be this distance minus this distance.
Mm-hmm.
So O to Y prime, or O to B minus O to Y, B to Y prime.
I think is the way we're going to want to do it. O to B minus O to y prime.
No, B to Y prime.
So we want to find
Thank you. Yeah, we're looking for O to y prime. So, y prime to B. All right. O to B, do we have a way to figure that out? I mean, I know that that's y. So I know that O to B times cosine of theta would give me
Well, you know-
y. But do I want to do it that way? Did you see something else?
I didn't.
Would you be able to use x prime because that's the same size as b to whatever that point up there is?
No, we can't use x prime. Wait, x prime is the same as to what?
X prime to be in that, yeah. Can we use that at all?
I just don't know how it helps. Let's see. There's my y.
Is the angle of b theta?
Oh, we want. No, that doesn't work.
Well, I think Jeremy had a good idea because you know what X prime is. Why not just substitute it in?
It just doesn't get us anywhere. Let's see. I think I drew my picture funny. Okay. I think I wanted it set up like this. I think I wanted this to come through y. There we go. So here's y. That now comes through like that, and here's my point B. And we can still calculate it the same way.
Is that perpendicular to that?
This is meant to be a right angle.
Oh, I see. Okay.
Okay, so now, and this has height y. So now, this length, O to B, is going to be our hypotenuse, y, times the cosine of theta. So O to B is going to be y cosine of theta, right?
Yeah.
Can you show that again? Sorry.
So we're looking at this triangle, this point, this point, this point. The hypotenuse of that triangle is y.
Oh, I see.
OB is y cosine theta.
Okay.
Okay, so now, last thing we need is y prime to b prime. Well, this right here is also theta, so it would be the height of this triangle if I knew the hypotenuse. And the hypotenuse, okay, I know the hypotenuse of this triangle is x. Perfect. So talking about this triangle now, do. The hypotenuse, this side, is x.
So minus sine.
So this side right here has side length x, right? So we're looking for this side right here. That is going to be y prime to b.
Okay, I see it.
Okay, so that's going to be x sine of theta. Okay, perfect. So those are our transformation equations. If we're talking about a rotation in Euclidean geometry, let me double check that. Y prime equal y cosine theta minus x sine theta. Good. So regular Euclidean geometry, there's our transformation equations if we're just talking about a rotation. And notice now that x squared plus y squared is going to be x prime squared plus y prime squared. Let's double check that. So we're going to look at x prime squared plus y prime squared. And we better get x prime squared plus y prime, or we better get x squared plus y squared.
Okay.
Right?
Yeah.
We expect Pythagorean theorem to hold in both cases. So x prime is equal to this. So we have x, not squared, x cosine theta, plus, don't let me write the wrong one, y sine theta squared plus y cosine theta minus x sine theta squared, right? That's equal to, when we square this out, we're going to get x squared cosine squared of theta plus 2 xy cosine theta sine of theta plus y squared sine squared of theta. That's just expanding out this term.
Yeah.
Plus, expanding out this one now, we have y squared cosine squared of theta. That times that, we're going to have 2 of those, so minus 2 xy cosine theta sine theta. And then that times that, we're going to have plus x squared sine squared of theta. Did I do all that right?
Yeah, I think so.
All right, 2 xy cosine sine, 2 xy cosine sine, those cancel out. Okay, so collecting my x squared terms, this is equal to, I'm going to factor the x squared out both those, so we have cosine squared of theta plus sine squared theta.
Oh, not just one.
That was this term and this term. And now we need to collect this term and this term, factor out the y squared, plus y squared times, we'll write the cosine first, cosine squared theta plus sine squared theta. And then, like you just said, cosine squared plus sine squared is 1. So it's equal to x squared plus y squared. Yay, it works. Okay? And so this quantity, x squared plus y squared, or x prime squared plus y prime squared, the sum of the squares of your coordinates is an invariant. No matter how you rotate it, that quantity, whatever it is, doesn't change. Whatever it is, a 1, reference frame is also is in another reference frame. Good?
Yeah.
Okay. So now, going back to our equations for light, well, do I want to do this all in one go? Or should I write these other ones out really quick? You've never come across the hyperbolic trig functions, have you?
No, I don't think so.
That completely ruins where I was going with this. Because for hyperbolic trig functions, should I just give it to you anyways?
Sure.
Alright, we'll just give it to you anyways. Hyperbolic trig functions, so rather than cosine and sine, you have cosh and sinh is what we call it.
Oh.
Cosh, and oftentimes we use a W for that, and we have sinh. So sine and cosine, but then put an H at the end of it to say it's a hyperbolic function.
Does it work the same way?
No, this by definition, oh my goodness. Let's see if I can remember. E to the x plus e to the minus x over 2, and this is equal to, or that would be put an x there, let's just put x. This is e to the x minus e to the minus x over 2, I think. If I'm remembering those right. But they're similar to sine and cosine function in that these will map out a hyperbola, the unit hyperbola, rather than mapping out the unit circle.
Okay.
Does that make sense?
What's
A hyperbola that goes from the origin, a unit 1. So if this is a unit 1, and this is a unit minus 1. I don't know. Let's plot some points here. We'll check to see if I did this right. What happens when we plug in 0 for both of these? So cosh gives us our x-coordinate, sinh gives us our y-coordinate. Same as before. So it's only going to do the top half, but plug in 0 to this, what do we get?
1.
We get 1 plus 1 over 2.
Oh, yeah.
So we get 1. And sinh here, we get,
Does that give you your x coordinate, or does it give you your t?
well, just in regular geometry.
Okay.
And I'm wondering if I have these right. Just Google really quick, hyperbolic trig functions. I wonder if I've got my sign switched here. Or just definition of cosh or sinh, one of the two, and then we can figure it all out from there. Let's see, if I plug in 0 for this, then we get 1 minus 1 is 0, so I'm getting 1, 0. Which seems weird.
It's cosh is e to the x plus e to the minus x over 2.
Okay. So I've got it right. Just kind of want to plug in a bunch of points there.
Yeah, you look good, I guess. I think.
It's a nice tie.
But now I think I'm missing something. My time?
You said you look good.
Ah. Well, whatever it is, we'll let it be for now. But so they should map out the same way that cosine of theta and sine of theta, cosine of theta and sine of theta. For any theta, they give me x and y coordinates on a circle. They should give me x and y coordinates on a hyperbola.
Okay.
On something that looks like this. I don't know if that one's going to be tipped sideways, because you can have your hyperbola up like this, or you can have it tipped to the side. Not sure which way it's going to come out. But that's what they do. So hyperbolic trig functions, that's why they're called that.
Okay.
You do hyperbolas. Okay, and just like we came up with our equations for rotations in the unit circle, we're not going to derive these ones, but we also have their equations. Now if you know x and y, then x prime is equal to x cos omega, to plug in is what we'll plug in there, minus y sinh omega, and y prime is equal to negative x sinh omega plus y cos omega. Not sure why I changed the order on those. So the ones we had before, just so you can see similarities and make their order match so you can see the translation and how they're closely related. And we have y prime is equal to minus x sine of theta plus y cosine of theta.
So it's basically the same thing.
So they're almost the same translation equations. You just switch that plus to minus. Looks like the only difference. And you would derive those in a similar way to how we just derived the rotation. The way that we derive these, you can also derive these.
Is your y prime right on your bottom one? Wasn't
Yeah,
it
we
minus?
just did cosine minus sine. I just wrote the cosine first.
Oh,
I
I
just
see
changed
the
the
negative.
order to help you see
Okay, I see it now.
how they're related better. Okay, so going back to our speed of light equation now, when we were talking about these diagrams, then the way that we modeled light was with the equation x equals t when the speed of light was just 1. Right? So x equals t would be our 45-degree lines. Here's x equals t, and that's in the special case where c is equal to 1. Speed of light's 1.
Okay.
Otherwise, it would have been x equals ct, right? But we want to leave that out. So x equals t is the equation of a light ray going forward. X equals minus t, or minus x equals t, is the equation for a photon traveling backwards.
Yeah.
In either case, they both satisfy the absolute value of x divided by the absolute value of t is equal to 1.
Yep.
Good? And so that gives us, there's two ways that this can be satisfied, that the speed of light can be 1, and that is if x squared, well, how's the best way to say that? When is this equation true?
When is it true?
Yeah, x and t don't necessarily have to be the same value, right?
When it's in seconds and light seconds.
When it's in seconds and light seconds, but when is it actually equal to exactly 1? That's when x and t have the same magnitude, when their absolute values are the same,
Yeah.
right? When you go 1 light second per second, or 5 light seconds per second, or negative 5 light seconds per second. So you need their absolute values to be equal. So maybe I should have said it this way better, and you'll see it better. Rather than x equals t, we just need x, the absolute value of x is equal to the absolute value of t. This is what needs to be satisfied for it to be a photon, for it to be light. Not just x equals t, that's just a photon traveling forward.
Yeah.
Because you could have also had a photon traveling backwards. So here's a condition that every photon meets. The absolute value of x is equal to the absolute value of t.
Okay.
Does that make sense?
I think so.
Which then gives us that x squared is equal to t squared,
Mm-hmm.
because now they're both positive values, which then I can write as t squared minus x squared is equal to 0, if I move it both to the same side.
Okay, that makes sense.
Now also, x squared equal to t squared, if the equation of the thing that we're talking about is a photon for you, then it's also a photon for me. A photon, however you measure a photon traveling, is how I measure a photon traveling. We both measure photons to have the same speed. The speed of light is the same as the speed of light. So if the absolute value of x is equal to the absolute value of t, that also implies that the absolute value of x prime is equal to the absolute value of t prime. Why do I keep doing parentheses?
Okay. that
For
makes
me
sense.
as well, right?
Yeah.
And so I'll also say that in my reference frame, x squared is equal to t squared, t prime squared, for a photon. Or I'll also say that t prime squared minus x prime squared is equal to 0.
So they're equal to each other?
So they're equal to each other. And so t squared minus x squared is equal to t prime squared minus x prime squared. So whatever you calculate here, I calculate the same thing here. We get the same numbers for these values. So any transformation we have has to preserve this equation for light.
Just like the distance in Euclidean geometry?
Just like the distance in Euclidean geometry. But this is specially for a photon so far.
Okay, that makes
So
sense.
far we've just said this, whatever our transformation equations are, they have to preserve this for a photon.
Okay.
Now we're rederiving these equations, coming at it a different way. I'm going to rederive these same equations. And we're going to find out that these equations that we end up deriving satisfy this.
Okay.
Just coming out through the hyperbolic trigonometry way.
Hyperbolic. Okay.
So we can write this out really quick. Well, I don't know if that's worth doing since you don't have the trig. But if we were to take that squared and we were to add it to that squared, we would get x squared plus y squared. Or, sorry, we'd get y squared minus x squared, depending on which word we get, sorry. If I were to take here and I were to do y prime squared minus x prime squared, I would end up with y squared minus x squared. We did the same exercise with this, but in that case we were doing y squared plus x squared prime prime was equal to y squared plus x squared. Right? We manually worked through that with these equations.
Okay.
If we were to do the same thing with these equations, we'd see that that is the same.
So your t's and your y's are the same?
So this is a quantity that is preserved when we do a rotation of a hyperbolic function. When we do a rotation of just regular Euclidean functions of the sine and the cosine, then this was preserved. Right?
I see.
We showed that no matter what theta is, this is always the case.
Yes.
You can always plug in up here to show that no matter what omega is, this is always the case.
Okay.
And so we observed that fact for hyperbolic functions, hyperbolic trig functions, and we observed that we want this fact for photons. And so it begs you to do something. Hyperbolic rotations preserve this quantity. We know that going from your reference frame to my reference frame, we have to preserve this quantity for light.
Okay, that makes sense.
So the thing that begs for is maybe what's going on from here to here is some type of rotation like this. Which it turns out it is.
But how would you rotate like that?
And picturing it in your head, no chance.
Just accept the math and move on?
What does a 5-dimensional room look like?
But this isn't necessarily a 5-dimensional room. This can be our dimension, right?
Yeah, we exist in space-time, but space-time is a 4-dimensional manifold.
So we can't see space-time?
I don't understand the
Like,
question.
we can't.
You live in it.
But if we don't see 4 dimensions, right? And it is 4 dimensions.
Right, but we experience 4 dimensions. We experience 3 dimensions of space and 1 dimension of time.
Oh,
When we mathematically represent it, it's with a 4-dimensional object. See, we save ourselves a ton of headache here by just saying we're only going to talk about your x position in time t. We don't talk at all about your y coordinate.
or your z coordinate.
And now try and imagine we plug in the z coordinate into there as well. And now you're in trouble.
Yeah.
Yeah. So there's lots of things that we can't picture, and it's hard to get good intuition for it. And you can look at videos online of people coming up with animations to try and help make these things make sense and give you pictures to look at to help appeal to your intuition.
Okay.
So one of the ways that they try to help appeal to your intuition when they draw hyperbolic geometries is a good intuition for a hyperbolic geometry is like a saddle on a horse. So kind of draw this out really quick to show you that distances can really quick be deceiving. Although it's not really the same thing as what we're talking about here, just good intuition in general. So the saddle of a horse looks something like this. It goes down and it comes back up, right?
Mm-hmm.
And on a saddle, so imagine I go from one side of the saddle at this point up over the saddle to the same side back to that point. I don't know how to say it. Let's also draw a bird's eye view of the saddle. So bird's eye view, just looking down on the saddle, is going to be a perfect rectangle. So that's looking down the saddle. If you look at it from the side, here's what the saddle looks like.
Okay, I see it.
Okay, so if we look at the distance from here to here, and we compare that with the distance from here to here, let's think about what those represent on the saddle. On the saddle, I'm starting over here, and I'm going up, over, coming back down on the other side of the saddle to this point here. That's this line, right?
Mm-hmm.
Whereas this one, I start here, hardly go up and over anything. And so this point is a lot closer to this point than this point is to this point.
Aren't they the same distance though?
No, sorry. Think about the saddle. We're looking down on the saddle. The saddle, on this end of the saddle, has a huge hump.
Okay.
So my point starts here, and it's got to go clear over the saddle to here. That's this line segment. If we were to draw that, draw the line segment. From a bird's eye view, it just looks straight.
Okay.
Now go down to the middle of the saddle where it's almost flat. And draw the same line segment. It's a way smaller line segment.
Yeah.
But from a bird's eye view, here's what it looks like.
Okay.
Yet this distance is a lot bigger than this distance.
That makes sense.
And so it would even be possible for me to draw a line on there like this, and it might be the case that this line is actually longer than this line. Even though from a bird's eye view, that definitely doesn't look like it's the case.
It could be.
It could be. It might not be. It might be.
Yeah.
The point is, you can't go, if this shape exists on the surface of a saddle, and apply the Pythagorean theorem like that. It doesn't work. It's not flat.
Okay.
So these geometric figures that we're plotting on, we can't assume that they have that flatness to them.
Oh, I see. Is that why yesterday those lines could be longer even though they didn't look longer?
It's intuition for it.
Okay.
It's intuition for it. And so in our weird geometry, things are just so curved that all the points that are equidistant are on a hyperbola, which seems weird. So just on the top half of a hyperbola, let me draw my light rays in. These are all the points the same distance away. And so it's like going from here to here, you have to undergo a ton of curvature. That's way steep down. Versus here to here, you're almost walking on just a straight line. Kind of.
Okay.
I know.
So it's the depths and the values in the space-time continuum of time with space? Or what is that?
Well, sometimes even talking about depth doesn't even really make sense. Just because your saddle isn't flat doesn't mean you now have notions of depth. As weird as that seems.
What is it?
Yeah.
Height?
Well, because you only exist on the object itself. So if you were a two-dimensional person who existed in a two-dimensional world, so you exist on this sheet of paper as a two-dimensional person, and you can go back and forth, back and forth. If the paper's like that or the paper's like that, you have no clue. If you're just two-dimensional.
You wouldn't care either.
Yeah, it makes no difference to you.
Okay.
And so it doesn't matter how the paper is warped. It doesn't matter if it's flat or not to you. Right? And the notion of how bent it is, how much does the paper stick out this way versus this way, doesn't really make sense unless you exist in a higher level geometry that the paper is superimposed into.
Okay.
Okay. That's the danger of that. Anyways, so we notice that hyperbolic rotations preserve this quantity. We notice that we want to preserve that quantity at least for photons. And so that's begging for us to use these hyperbolic functions. And so that was the insight somebody made to realizing, oh, these might just be rotations in a hyperbolic geometry. Okay. Should we go through the derivation? I feel like it's not doing you guys very much good because we already know the endpoint. So we'll leave it there with that. We won't rederive the Lorentz transformations from this. Playing around with the hyperbolic functions, we could, and we could come up with these exact rotations.
So the rotation
We'll just
does
jump
say-
to the. We'll just jump the gun here and show that these rotations preserve like this.
Okay.
So let's just show that to make sure that that's clear, and then that will say is sufficient to say we can think about these as a hyperbolic rotation. Does that make sense? What I'm saying?
Mm-hmm.
Yeah. I don't like doing a lot with the hyperbolic functions. I should have been more prepared to work with them today than I am. And since you guys haven't worked with them either, you can't really make sure I'm not making mistakes as I go.
Yeah.
So we'll jump to the chase. Okay, so let's just look at t prime squared minus x prime squared. T prime squared minus x prime squared, what do we get? So t prime squared, looking over there, we have t minus vx, we're going to ignore the speed of light in these computations,
Okay.
squared over 1 minus v squared, right?
Mm-hmm.
And we're going to minus from that. For x, it's x minus vt. We're going to have that squared all over 1 minus v squared. Right? So let's multiply that out. We're going to get t squared here minus 2vtx plus v squared x squared. That's multiplying out this one. Now multiplying out this one, each term, remember, I need to put a minus sign on it. So we start with a minus x squared. Then we're going to have plus 2 vtx, and then we're going to have minus v squared t squared. Right?
Okay.
Did I mess anything up?
This ultimate equals 0. Ultimately equals 0, right?
No, it better equal t squared minus x squared.
Oh, I see.
This is something that we should agree on no matter what. This is our invariant. This is, you and I might not agree about t, and you and I might not agree about x. But you and I always and forever will agree about t prime minus x, or t squared minus x squared.
Yeah.
The same way that in Euclidean geometry we all agree about x squared plus y squared. Here we're always going to agree about t squared minus x squared.
Okay.
That's what we're showing. Okay. So minus 2vtx plus 2vtx, that cancels with that. All right, we got that. This is equal to, let's collect all our x, well, we'll do our t terms first. So we have a t squared minus v squared t squared. So factor t squared out of that. So we got t squared times 1 minus v squared. Plus, let's look at all our x terms, or minus. And let's look at all our x terms.
X squared.
So we have minus x squared. From here, we're going to have a 1. And then from here, since we factor out a minus sign, then that's going to be minus v squared. You see that?
Yeah, I see.
Negative, negative gives us back the plus we had. All over 1 minus v squared. and la da da, we get t squared minus x squared.
Okay.
So with these Lorentz transformations, you and I don't agree about t, you and I don't agree about x, but for sure, whatever I call t prime minus x prime, t prime squared minus x prime squared, you also call t squared minus x squared. So you and I both agree, take our time, square it, minus our position squared, and we get the same value.
Okay.
And that's our distance function. This is the equation of a hyperbola. Y squared minus t squared, if we're using that picture, t squared minus x squared equals some constant, is going to be some hyperbola, just on the top half of it. Some hyperbola where whatever that constant is, some constant will say little a, then little a is going to be right there, and it's going to be the hyperbola that goes like that. And so every point on that hyperbola is little a away with our new way of calculating distances.
Gotcha.
And so you and I will agree that all these points are a distance little a from the origin. Whether it's your frame or my frame, if we were to pick any of the points on that hyperbola, find it in your reference frame, find it in my reference frame, calculate its distance from the origin, we would get the same value. The same way that no matter what our reference frame was, if we were calculating the distance from the origin, so back to geometry, there's your frame, here's my frame, pick a circle, pick any point on the circle, you and I will agree on its distance from the origin.
Yeah, that makes sense.
So over here, pick a hyperbola, you and I will agree on its distance from the origin.
Okay.
With this new funny metric of a minus sign rather than a plus sign. Make sense?
Yeah.
So that's the invariant. So yes, space is relative. Yes, time is relative. Distances in space-time? No, they're not relative.
Distances in space-time?
Yes. This is how we calculate distances in space-time. This is the metric that we use. Now really we use the square root of that. So we have a value that we call proper time. Proper time, we use a tau to represent it. Tau is equal to the square root of t squared minus x squared. And that's your distance. Same way that we take a square root for the Pythagorean theorem to talk about your distance.
Yeah.
We use tau here to talk about this distance, and we call it your proper time.
So what exactly is space-time?
It's, you got space that way, you got time that way. It's that surface that we're talking about.
Okay.
I mean, an actual space-time, I can't give that to you. Because it's a type of manifold, at the very least.
And we don't know manifolds.
Right. I can't give you what space-time is from the ground up. That's classes worth of lectures, as in multiple classes, like Calc 1, Calc 2, Calc 3, multiple classes.
Okay.
So what is space-time? It's a mathematical model that we use to model the phenomena of our universe. Simple as that. Okay. Let's see. So we talked about space contractions, talked about time contractions, talked about proper time. Oh no, now we're talking about proper time. Okay, so why do we call it proper time now? Let's get intuition for that, and get at least one intuition for what this quantity gives us. Wouldn't that be nice?
Okay.
Okay, so here's your reference frame.
Okay.
Here's a photon in your reference frame. Two photons shot out from the instant that you decided to start your stopwatch, right?
Okay.
Pick some point in that reference frame.
Anywhere.
Anywhere. And so now, here's your t coordinate, here's your x. This has coordinates x, t. And you want to determine, and you want to know the proper time for that. Why is it called proper time? So once you pick a point, now we're going to draw the path of some moving observer in your reference frame who goes through that point. So you pick some point, and now I'm going to make sure that I go through that point. I'm going to walk at such a speed that I definitely go through that point. Okay? So whatever the velocity is that I need to walk through that point, I now walk with that exact velocity from this time over to that point.
Starting at the origin?
Starting at the origin.
Okay.
So we worked this out ahead of time. I got the speed down. I knew exactly how fast I was going to walk. You showed me the point. You showed me where, and you told me when. You said you got to be there in 10 seconds. And go. And I made sure that I was exactly there in 10 seconds. Okay. Kind of a contrived scenario, but just trying to give you intuition for why we call this proper time. All right. So in your reference frame, this is x equals vt. For me, this is x prime equals 0. Right?
Oh, yeah.
So you calculate now your distance to that point. Your distance to that point is going to be your times coordinate squared minus your position coordinate squared. Right?
Okay.
And that has to also be equal to my time coordinate squared minus my position coordinate squared. But what is my position coordinate in this contrived scenario?
X prime.
But what is my position always relative to me?
0.
0. So x prime relative to the moving observer is always 0. So in this special scenario, what you calculate as t prime minus x prime will just give you the t prime for me.
But what is that t prime for you?
T prime is how many seconds I measure off.
10 seconds.
So take the square root of both sides, and so we get t prime is equal to the square root of t squared minus x squared. So t squared minus x squared at some point gives you the amount of time a moving observer would experience getting to that point. It's calculating the amount of seconds the moving observer experiences.
The moving observer.
Yes, and so we call it proper time. It's the time that the moving observer experiences to get to that point.
So it always depends on the moving observer.
Well, that's just where proper time comes from. How do you always and forever calculate t squared minus x squared? Why do we call it proper time? Because for any point you can do this scenario. You can set up this scenario, and then it gives you the time experienced by the observer along this path.
Oh, I see it.
And so we call it proper time.
Yeah,
That's the
that
name
makes
of it.
sense.
But it's just a metric. I just want you to get a sense of why we call that proper time. And it's because for any point we can come up with this contrived scenario, and then it ends up just giving us the time. It always, so anytime you calculate t squared minus x squared for some point, you are calculating the time that the moving observer would experience had they gone once they got to that point, assuming that you both start from the same origin.
Okay.
Does that make sense?
Yeah.
That's why it's called proper time.
Does that mean you experience more time or less time?
Do I experience more time or less time than you?
More.
Who are you?
Take your time.
Who's
I'm
moving?
moving.
Is that t prime?
I move. Prime is moving. You're holding still.
Oh. So yeah, you experience. No. I thought
Less.
prime was moving.
How is that less?
No.
Take your time. Look. Just look at this equation.
No.
If x is positive, what's bigger? T or t prime?
Can you say
T
that?
prime.
Okay. There you go. Huh?
Can you explain what t prime is?
T prime is the time coordinate for the moving observer.
Why did you get rid of
To
x
that
prime? I thought x prime was
Because
standing
x prime is 0 along this line.
I thought it was standing still. How is that 0?
Look. When I'm walking with constant velocity v relative to you, wherever I am, I call coordinate 0. I don't move relative to myself. Look, going back and forth between this picture and this picture. Here's your view. Here's my view.
Okay.
I always view me as not moving.
Okay.
So what you call x equals vt, I say, no, 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 that's x prime equals 0. So along this line, x equals vt, for the moving observer along that line, their x prime is equal to 0.
Why do you have those dashed lines going to the origin?
This one and this one?
Yeah.
Because those are photons and habit. You always throw your photons on there first thing when you draw these things. It's kind of like adding the ticks when you draw your xy coordinate systems. You draw your photons in there.
Okay.
Because any hyperbola that you draw, hyperbolas have asymptotes. And so any hyperbola, this is the asymptote that the hyperbola approaches. And so they get closer and closer to those lines.
Okay.
Right? So you go into the scenario why we call it proper time for a second.
For a second.
You're saying that the faster you go, the more time you experience.
The faster I go in your reference frame, the less time I experience in your reference frame. If you were watching my clock ticking as I'm moving, the faster I go, the slower you see my clock ticking.
What about your reference frame? Is it the same?
My reference frame, I see everything backwards. You're the one moving relative to me. My clock looks normal. Your clock's going slow. There's a symmetry here.
Okay.
So in your reference frame, my clock's ticking slow. My clock's ticking slow. Slower than yours. And so what you're calculating when you do t prime squared minus x prime squared, or t squared minus x squared under the radical, you're calculating the amount of ticks you'll see my clock tick.
Yeah, that makes sense.
What's t prime?
Huh?
What's t prime?
The amount of ticks on my clock. Because if I were to do the same thing, if we flip the scenario around, and so now I was calculating it for you, then I would calculate that your t is equal to the square root of my t prime squared minus my x prime squared. Sorry, not the squared. And that would be calculating the t going from here to here.
Yeah.
Okay.
So t prime squared minus x prime squared, pick some coordinate, and it calculates the time of the moving observer through that point if they start at your origin. And that's why it's called proper time.
Proper time.
That's where it
That
gets
makes
that.
sense.
Now, this only works if
Okay.
if we pick nice points. We can pick bad points.
What's a bad point?
Yeah, maybe before we talk about the bad point, let's notice something very strange. So back to regular Euclidean geometry. 2 points are a distance 0 apart if and only if they're the same point.
Mm-hmm.
Right? What about over here? If the metric that we use to calculate distance is t squared minus x squared, so that's how we're calculating distances now, right?
Okay.
When is that 0?
When
It's 0 when they're both 0. That's one example, which is the only time you get 0 in Euclidean geometry, right? In Euclidean geometry, it's t squared plus x squared under the radical if we want distance, but really the square root of quantities is all we care about, right? Here's distances in regular Euclidean geometry. Here's distances in the weird space that we're working in.
Okay.
This is 0 only when t and x, when we talk about the distance between 2 points, I made a mess out of this. The distance formula in Euclidean geometry, let's just write that out so we make sure I'm not confusing you at all. It's y2 minus y1 squared plus x2 minus x1 squared, right?
Mm-hmm.
And so the distance is 0 only when you're talking about the same point. Right?
Yeah, that makes sense.
Okay. So for us, when we calculate our distance, this just gives us the distance from our origin. we use t squared minus x squared. That's just the distance from our origin. I could do t2 minus t1 squared minus x2 minus x1 squared, but this is just the distance from our origin now. Okay, when we stick it under the radical. But when else can we get 0 here? They can both be 0, that's one way we get 0. How else can we get 0 there?
Every time they're the same.
Every time we have the absolute value of t is equal to the absolute value of x. When does that happen?
All along the photon
Twice.
line.
Where?
All along the photon line.
Light! When it's light. Light moves that way. So light, these photons, are at the point where the distance is 0 along these lines.
Where distance is 0?
Yeah, the distance from here to here is 0.
What? How is it 0?
Because they don't experience time or distance.
Oh, that's right.
Yeah, photons don't experience times and distances. That's one thing that we calculated. With length contractions and time contractions, we saw that their contractions go to 0 in both cases. But now we see it another way. This distance that we measure is 0 for photons. So if you want the hyperbola, where everything's a distance 0 away, then that special hyperbola is an x. It's the steepest hyperbola you can get.
Oh. So it's like the cone thing, except it actually
Yes.
goes to point.
You pick the cone, you pick the hyperbola right through the center of the cone.
Okay. That makes sense.
That's the limiting case. And anywhere else, then you'll get hyperbolas that get closer and closer to this cone. So light has a distance 0. Anything up here has a positive distance when we use this positive distance metric. What about a point over here? A point over there, we now have x is bigger than t.
So it's a negative distance.
Well, it's under a radical.
Oh, so it doesn't
And
work.
so it just turns out the majority of the time we're interested in points up here, so we have a notion of proper time. When it's a point over here, then we switch our metric and we say, okay, now the way that we're going to calculate distances is the square root of x squared minus t squared, and we're going to call it instead proper distance.
Okay.
And we call points up here are time-like, and points down here are distance-like. Time-like points are points that it's possible for you to get to. Distance-like points are points that are impossible for you to get to.
Yeah, that makes sense.
It is impossible for you to get, if this is a distance right here of 10 light years, 10 light years, and this right here is a time of 1 year, that is a point that is impossible for you to reach. You can't go faster than light.
Yeah, that makes sense.
That make sense?
That does.
And similarly, a photon from this event, notice, the fastest it goes is right like that. And so it won't be until you experience this much time that an event here could have even affected you, that you could even see that event.
If that's in 0 time.
Well, no, that's way down the road.
Oh.
This was 1 year,
Yeah.
might be 50 years down the road. Well, in our special case, it's going to be 9 years down the road.
Gotcha.
Good? Okay, so last thing I wanted to do is use this to show you now why we can't go faster than the speed of light. So I want to go back to one of our weird examples, which was the example of if I'm on a really fast train made out of glass, and so I'm going half the speed of light, and then I turn on a flashlight and it shoots a photon out at the speed of light, how fast do you see the photon going? Better be at the speed of light. Let's do this calculation real quick.
Okay.
You see what I'm saying?
Yeah.
So we'll use Lorentz transformation for this. So we're going to set up 3 scenarios. We won't quite do that photon one yet. We'll do something more general, and then we'll do that as a special exception. So here's a train, glass train. Glass train is moving this way with velocity v relative to you. Here's you. You're standing out here, watching it, watching the train go by. Me, I'm standing inside the train. Right? I'm very happy about this arrangement.
I'm sure.
Now, inside of the train, since I'm using the train's reference frame, then here, inside of the train, we're using t prime, x prime coordinates. Now here, you're measuring everything with t coordinates and x coordinates, right? And now, inside the train, I got one of my kids and they're in like a little kiddie car. Whatever. And there's a little kid in the train and the little kiddie car having the time of their life. And they are now traveling with a velocity u. That way. And they have their own reference frame, which is moving with them. So they have their own reference frame, which they use to talk about the world, t double prime, x double prime.
Okay.
The question is, what velocity w do you ascribe to my little toddler? I'm moving at a velocity v relative to you. They're moving at a velocity u relative to me. What velocity w are they moving at relative to you?
V plus u.
No. If that were the case, we could break the speed of light. So we're going to have to use our Lorentz transformations to figure out this equation. Does that make sense? Make my train a little shorter. Hopefully I can figure this out. Okay. So I want what my kid calls 0 in your reference frame is how fast they're moving. Okay, so, sorry, I'm gonna have to kind of think through this with you guys as we go. So x prime, to get my coordinates from your coordinates, is going to be, why am I already blanking? That's not a good sign. X minus vt, all over the square root of 1 minus v squared. And t prime is equal to t minus vx all over the square root of 1 minus v squared. That's how we get from my coordinates to your coordinates.
Yeah.
Now, how do we get from my child's coordinates to my coordinates?
I would assume it's the same thing.
It's
Just
the same thing.
yeah.
X double prime is equal to x prime minus ut. Remember, they're moving at a velocity u relative to me.
U t prime.
Oh, thank you. T prime. All over the square root of 1 minus u squared. And then t double prime is equal to, maybe we don't need t double prime. I'll write over here in case we need it. T double prime is going to be t prime minus u x prime all over the square root of 1 minus u squared. Okay, so what we're interested in is how fast my child is moving in your reference frame. Now, my child's position, according to them, is x double prime equals 0.
Okay.
That's where they are, to them.
Yeah.
So we need to convert that equation. We need to rewrite x double prime equals 0 using your coordinates. Then that will tell us how they look in your reference frame, and we can figure out their velocity.
Okay.
So x double prime equals 0. That's going to be some line like this in your reference frame. So x equals omega t, or wt, will be the same thing as x double prime equals 0. And we'll figure out what that line looks like in your reference frame.
So you just make 0 equal to that equation?
Well, let's substitute in really quick. So x double prime, just substituting in. X prime is going to be, I'm going to do the denominators. Let me just do we'll just do the denominators last. Okay.
Okay.
So ignoring the denominators for a second, plugging in x prime, we're plugging in x minus vt for x prime. So we have x minus vt. That was x prime. Now we need to subtract u times t prime. So minus u times t, so minus ut, and then minus u times minus vx is plus vx.
UVX.
Thank you. And then this is all over, both these have the same denominator, right? So I can factor that out and then multiply by this one's denominator. So that's all over the square root of 1 minus b squared times the square root of 1 minus u squared. Good?
Yeah.
So that was just substituting in. Now I want to know where this is equal to 0. So forget the numerator, or forget the denominator. This is going to be 0 wherever the numerator is 0.
Yeah.
So we are just interested in where x minus vt minus ut plus uvx is equal to 0.
Okay.
Okay, so put all my x's on one side, all my t's on the other side. Because I want in the form of x is equal to my velocity times time.
I see.
Okay, so we'll leave my x's over here, we'll put everything else over there. So over here we have x times 1 plus uv is equal to, when we move that to the other side and that to the other side, then we're going to get t times u plus v. Did I do that right?
Uh-huh.
So now we have x is equal to u plus v over 1 plus u times v times t. You see that? And so this is our w. W is equal to u plus v all over 1 plus uv.
No.
Well, just the speed. Speed times time gives you distance. Okay? Now, if we were to plug back in the speed of light here, the way we do that is we basically just need to make our units make sense once again. Right?
Gotcha.
So we have a velocity there, we have a velocity there, divided by 1 plus a velocity times velocity. Uh-oh, we can't have that. The bond needs to just be a constant. Can't have units.
So how do we get it like that?
We divide by c squared, exactly.
Oh, I see. Okay, that makes sense.
Okay. So just to give you a sense of the difference between what one person says and what another person says, first off, let's think about low speed. Because you wanted the answer w equals u plus v, right?
Yeah.
That's good old Euclid. Or, what? That's good old Galileo. Okay. So let's see how well that actually works. So let's let u and v both be 3 million meters per second. Huge speeds, right? Or in other words, 1% the speed of light.
Okay.
So rather than using this, I'm just going to write it in terms of the speed of light up here and just use 0.01 rather than 3 million and plugging 3 to the 8 there.
Yeah.
Right? Write everything in terms of units of the speed of light. So then in that space we get w is equal to, we have 0.01 plus 0.01 all over 1 plus 0.0001. Which is going to be equal to 0.02 divided by 1.0001, which is essentially 0.02. Makes
Yeah.
almost no difference.
So when you get higher, it starts to really make a difference.
How high do you have to get for this to start making a difference? Let's try another one. Let's say you're going 90% the speed of light. That's super fast, right?
Yeah.
Let's see how much of a difference it even starts to make there. So we have 0.9 plus 0.9. So make sure we understand the scenario that we're setting up now. Well, now it better make a huge difference. So that was slow speed. So now high speeds, here's the scenario we're setting up. So now I'm on a train going 90% the speed of light.
Yeah.
And my child is in a little car, and it's an amazing car, because it can also go 90% the speed of light.
Okay.
You see that?
Mm-hmm.
Now, good old Galileo would say, uh-oh, that means that your child is going 1.8 times the speed of light relative to you.
Yeah. But that's not the case.
All right. So we get 0.9 plus 0.9 all over 1 plus 0.9 squared now, which is going to be 0.81.
Yeah.
So this is going to be equal to 1.8 divided by 1.81, which is really close to 1. So you outside the train, how fast do you see my child going?
The speed of light.
Almost the speed of light, just slightly slower.
Yeah.
Okay, now let's get crazy with it. I'm in a train going 90% the speed of light, and I'm going to turn on a flashlight and shoot a photon.
Going 100% the speed of light?
Photons travel at the speed of light. Light travels at the speed of light, every time.
Yeah.
So, in that case, u is going to be 1, but v is just my speed. We'll ignore my speed for a second. We'll just plug in 1 for u.
Okay.
So I'm traveling some speed v, but u is 1. So I should turn on the flashlight, and I'm traveling some speed v, who knows? How fast is it going? Well, that's going to be 1 plus v times u times 1, or 1 plus v.
So just 1.
So just 1. So it doesn't matter how fast I'm traveling. If I turn on a flashlight and shoot a photon, you always see it come out as 1.
What if you go faster?
Faster than what?
Like 1.5 times the speed of light.
What if I was already traveling faster than the speed of light?
Yeah.
Then everything's broken. Notice what happens down here if you plug in velocities greater than the speed of light. So no, you can't go the speed of light. And you can do this recursively. If I got a train traveling 99% the speed of light, and inside that train, I had a train traveling 99% of the speed of light, and inside that train, I had another train traveling 99% the speed of light, and inside that train, I had another train traveling 99% the speed of light, and I was standing in that train, I'm still not going the speed of light. I'm going to be going some small fraction of it.
Yeah.
Not a small fraction of it, I'm going to be almost going it. Some small fraction away from the speed of light. So you can't travel the speed of light.
You can't travel more than the speed of light. Can't you travel the speed of light?
I know of one way to make you travel the speed of light.
Become photons?
Yeah, vaporize it. If that's still you, then you're traveling the speed of light.
Awesome.
Now you can't accelerate mass to the point that it travels the speed of light. So we won't do it, but you could do similar mass where you calculate you know kind of how we had to calculate, well, no, that's not really true. Shouldn't say that. But it takes infinite energy to accelerate an object that has some rest mass to the point that it's traveling the speed of light.
Okay.
So whatever the equation, if we were to derive some equation for it, we'd see that as we plug in the acceleration necessary to get us the speed of light, then our equation goes to infinity, calculating the energy for it. So you can't have any object that has what we call rest mass traveling the speed of light. Rest mass?
Rest mass?
It's usually what we mean by mass. So you'll hear two things. You'll hear photons are massless particles, but then you'll also hear that photons are bent by gravitational fields because they have mass. Right? A bit of a contradiction there.
Yeah.
What we mean when we say that photons are massless particles is that photons have no rest mass. If you were to stop a photon and make it hold still, it wouldn't have any mass. Now you can't stop a photon, so a photon, if it exists, it has to be traveling at the speed of light. There's no such thing as a photon holding still. That's an impossibility.
Mm-hmm.
But all its mass is in the fact that it's moving. If it were to hold still, it had no rest mass. If you tried to stop it, it wouldn't exist anymore.
Okay.
You, on the other hand, you have rest mass.
Yeah.
And that's what we typically mean by mass is rest mass.
Okay.
Okay, so that's good enough intro into special relativity. Give you a sense for it.
Just hurt my brain the whole time.
Yeah, that's one of the great things about special relativity. Simple math, super complex concepts. And it's one of those rare occasions that you get that. Because usually it's simple phenomena, super hard math. right? I drop this stupid thing, and we just take into account air resistance. Calculate how it falls.
Yeah.
It just got super complicated, and the math kind of blows up. Right?
Mm-hmm.
But our understanding of it, really simple. Special relativity, all we used so far was algebra.
Yeah, we never even
For
used
everything.
calculus.
We didn't touch calculus. And so it's a great way to make you understand that you came across a lot of problems where the math got really hard. That doesn't mean as you continue on to more complex ideas in physics, the math necessarily has to blow up like that. And so there's a lot of physics out there that you can come to understand right now by just going and studying it. And you don't need to understand all this deep, complex mathematics to start understanding it. And yeah, now you can go watch a ton of videos on special relativity, and they'll do a much better job than me and catch all the things I said wrong. Because again, I've never even taken a class on this stuff. Keep that in mind.
Oh, you haven't?
No, I haven't.
Oh.
Einstein's paper on this is very readable though, and it's only like 20 pages long. He has some terminology in there that you have to get used to. You might be used to most terminology now taking a physics class. And he makes mention to Maxwell's equations, which you take those in electricity and magnetism. But they're just reference stuff. I think that you could actually read the paper and be pretty much fine. And it's not a big paper, it's small.
And he published it by that?
Mm-hmm. Yeah. It's a 1915 paper. Yeah, so you can go read it. It's not hard at all. And he'll be talking about, the first part of it, we'll be talking about this exact stuff right here.
To show that speed of light is constant?
Well, no, the speed of light is a constant is a given, so that's one of his postulates.
Oh, that's right.
His first postulate is the speed of light is a constant. His second postulate we loosely call Galileo's principle of relativity. Anyways, that's that.